All right. So I'm going to give about a minute or two more for you to finish this. Couple of reminders. If you haven't already done so, make sure you get those. Make sure, or if you weren't here on Friday, remember that. Go back and look at the assignment for Friday. I gave you opportunity to make up some grades of it if you've missed some things. So make sure you get those test corrections in. For a lot of y'all, that will help your DHS score. Make sure you go back and redo the ionic and covalent test. I have it set up a little bit differently so that you can really get the points. I have it set up to where it's trying to seek for you to get an 80% mastery. So, just kind of go through, take advantage of the opportunities that I'm giving you. Oh, sorry, I didn't see you there. I need to lower my paper just one little bit. All right. So again, make sure you're taking advantage of those opportunities. I have about three paper grades that I've finished grading that I'm probably going to drop in at fourth period today into the grade book. Most people were doing well. I did see a common error in one place that I'm going to talk about today. It was on the empirical molecular sheet, but and I may end up talking about it tomorrow because that's when I plan on giving it back out. But there was for the most part, everybody's doing well with empirical molecular, but there was one little common mistake that I was seeing. And that's fresh. All right, so there's another leak right there. All right, with this, and we're not going to, the mistake we're not going to see on today's stuff because it doesn't do it. But I'm going to point it out just so that I can remind you. All right, anybody need more time for the bell ringer? Okay, I'll give you just a few minutes or a few seconds. All right. All right. So the problem that we're looking at today, and this is where we ended up for Chapter 6. This was kind of like the ultimate goal for Chapter 6, being able to do this. And it combines just about all the skills that we have from Chapter 7. Being able to understand what a percent composition tells us when it talks about percent ratio of elements in a compound, being able to go from moles to mass, being able to use a molar mass, and then relating it to the chemical formulas, which we did in Chapter 5. So when we're looking at this, it says we have a compound with the molar mass of nicotine is 162 grams per mole. All right, so we're going to use this, but we're not going to use it right away. This is going to be our molecular formula mass. And then it goes on to tell us that nicotine contains 74% carbon, 87% hydrogen, and 17.3% nitrogen. So I want to know the empirical formula and the molecular formula. Since I'm asking for both, I have to do both steps. All right. So going through there, it contains carbon, hydrogen, and nitrogen. So I'm going to convert that 74% to 74.0 grams. I'll convert the 8.7% to 8.7 grams for hydrogen and 17.3% for nitrogen to 17.3 grams. Now, to get from mass to moles, remember, I have to divide by the molar mass. So here I'm dividing by 12.01, and that's going to give me 6.2. The reason why I'm using 2 sig figs in my moles on this one, and it doesn't matter as much, but the reason why I use 2 sig figs there is just because I had 2 there. All right, that was just a mental thing for me to practice sig figs. But ultimately, we're trying to get to a whole number in this, so sig figs are not as important. And I would say more numbers here is better. All right. And then to get hydrogen, I divide by 1.01 because that's my molar mass of hydrogen. And nitrogen, I divide by 14.01. Now, I do that, I get my moles. 1.2 is my smallest amount. So essentially, I'm dividing everything by 1.2. Now, when you do this one, you get like 5.117, something like that. You get 7.1 something there, and then you get a 1 there. So my empirical formula ends up being C5H7N. From there, I can get my empirical formula mass, which I put here, because remember, we take molecular formula mass divided by empirical formula mass to get our multiplier. So my empirical formula mass, 5 carbons, 7 hydrogens, and 1 nitrogens equals 81.1 or ish, depending on how you round it. And then my molecular formula mass was given in the problem, so 162.1 divided by 81.1, and I get 1.99. Now remember, I'm looking for a whole number, so that 1.99 is close enough to 2 that I can just say that it's 2. All right. So when I do that, I'm going to multiply this 2 by everything in here. So 2 times 5 is 10. 2 times 7 is 14. 2 times 1 is 2. So my molecular formula is C10H14N2. Now, the thing that I'm going to point out tomorrow from the empirical molecular sheet is make sure you're paying attention in this region. You'll rarely get a decimal like this, like that's not able to be rounded here. But sometimes you'll get a decimal here that's not able to be rounded. So like instead of being 5 here, what if it was like 5.5 here? Remember, we would have had to multiply everything by 2. All right, that's the error that I was seeing in common on that sheet that we did in class on Thursday to turn in, that empirical molecular. And I'll point it out. It was one specific problem that had it. But I just want to make sure that we're aware that that happens. They like to put that version on the test, that version of a problem. All right. So our goals today. We are going to be doing chemical reactions this week. Our balancing chemical equations is kind of the theme for it. So our goal for today is to be able to write a balanced symbolic equation. When I say symbolic equation, you're going to see me use a couple of different words. Sometimes I will say skeleton equation. Sometimes I'll say symbolic equation. Sometimes I'll just say balanced equation. When I say that, what I'm meaning is using the chemical symbols like C for carbon, AR for argon, things like that. All right, so write a balanced symbolic equation from a word equation. We're going to be able to describe chemical changes by developing a word equation, balanced formula equations, and net ionic equations. We should also be able to relate the law of conservation of matter to the rearrangement of atoms in a balanced chemical equation. So every skill that we've done pretty much from chapter 4 on is kind of getting reused. We have to be able to understand why chemical formulas are written a certain way. We have to understand why we can't change subscripts in a chemical formula once we've written it. We have to understand what coefficients mean versus the subscripts, all of those things. So they're all important to be able to do that. So on your paper, on your desk, I passed out this sheet. What I would like for you to do is go ahead. We're going to look at what we already know. So take a minute. I want you to do just part A for right now on it. So take a minute or two and go through, follow the directions of what it tells us for part A. It says circle each of the subscripts in each chemical formula, draw a square around the coefficients, and then answer the questions for each of these. Yes. All right. All right. So everybody should have had enough time to kind of do this. So let's go ahead and look up here. All right. So the subscripts, again, drawing the circles around them. So the 2 in O2 is a subscript. The 2 in CO2 is a subscript. The 2 in H2 is a subscript. In C2H6, the 2 and 6 are subscripts. In Na2SO4, the 2 and the 4 are subscripts. For coefficients, we only had three coefficients, the 5 in front of H2, the 2 in front of C2H6, and a 2 in front of Na2SO4. Now, again, skills that we should have. We should be able to look at the symbol O2 and recognize that as oxygen. It's a diatomic element. So recall that. For CO2, it wants to know how many atoms of each are in there. So I have 1 carbon and 2 oxygens. Remember, the subscript only goes with the element that's immediately in front of it. And then for the next one, when we include a coefficient, that tells us that we have multiple versions or multiple sets of that molecule or compound. So I have 5 H2s. So if I'm looking for hydrogen atoms, I have 10 atoms total because the 5 multiplies by the 2, giving me 10. Same thing, I have 2 C2H6. So that means in total I have 4 carbon atoms because 2 times 2 is 4, and I have 12 hydrogen atoms because 2 times 6 is 12. And then going into the last one, I have 4 sodiums. I have 2 sulfurs because it's at 1 there. And then I have 8 oxygens. Any questions about those? All right. So if not, let's go ahead and move forward. So what we want to be able to do is use those compounds in a chemical reaction or a chemical formula. So the first thing we want to be able to do is write a chemical formula and know what a chemical formula is. So chemical reaction, and I should say instead of formulas, I should say now, instead of writing out reaction all the time, I'm going to start abbreviating that as RXN. But reactions, in reactions, formulas represent what occurs in a chemical reaction. All right. So we have 2 main parts of a chemical reaction. We have the reactants, which are the participants in the chemical reaction. Typically, the reactants are going to be on the left side of the reactants are going to be found on the left side of the arrow. All right. And then the other part of a chemical reaction we call the products. And if the reactants are on the left side of the arrow, where do you think the products are found? On the right. All right. And I'm going to start calling the arrow something specific, but I want to define it first. So, so we'll get there. Now, we can treat a chemical reaction just like a math problem, except for it's all symbolic. So it'd be all variables in our case. But we have certain meanings with those things. All right. So chemical reactions, in chemical reactions, formulas represent what occurs in the reaction itself. All chemical reactions will have a generic format. It's going to be something like A plus B reacts to form AB squared, something like AB with subscript 2 or something like that. All right. And then, you know, we're going to have more information. So like to do that one, to accomplish that one, I would need a coefficient of 2 in front of that B and all of that. All right, so there's just some generic information that we can have. There's generic setups to these formulas that we can look at and all of that. All right. Does anybody need more time? All right. So, if we have a chemical reaction, what are some products, or what are some evidences that a chemical reaction has occurred? So I want you to take a minute and I want you to think about chemical reactions that maybe I've shown you in this class or something like that, that you can determine what are the evidences that a chemical reaction has occurred. All right, so again, based off the reaction we just saw, what are some evidences that we saw a reaction? All right, color change, bubbles maybe, evolution of a gas. We definitely saw a gas being produced because we can saw the smoke coming off of it. Formation of a precipitate or a solid. We didn't see this fourth evidence in this one, but we saw the other three. All right. So you're not always going to see all four evidences in the same reaction, but it'll always have some evidence of the reaction that something is occurring. And like I said, if I would have put a thermometer in that reaction, you would have saw a temperature increase. This one is definitely an exothermic. All right. So again, we can look at different reactions and see different things occur. So in a reaction between sodium and water, what's going to happen is, and it might be better for me to write water as HOH this time rather than H2O. The sodium wants to be with the hydroxide more than the hydrogen does. So the sodium comes and kicks out the hydrogen and becomes sodium hydroxide, which we're going to say is aqueous. And I'm going to talk about what that means in a minute. And then we get H2 gas. So the smoke that you saw coming off was just H2 gas. The liquid that's left over is sodium hydroxide. Now, sodium hydroxide is normally colorless in a colorless liquid. I put something in there that indicates a base. And sodium hydroxide, if you remember when we defined a base last week or week before last, bases have hydroxide and end in OH. So the reason why it changed to that pink color is because sodium hydroxide is a strong base, and that just let me know it was there. Now, sodium is a solid, water was a liquid, this is a base, this is an aqueous, this is a gas. All right, so now, question? This is not balanced yet. All right, so be that 2, 2. Yeah, we're going to end up having to balance it. I just didn't get there yet. All right, so when we look at this and when we look at any chemical reaction in the real world, experimentally, we're going to look for evidences. We're going to look for change in temperature, bubbles, color change, formation of a precipitate, things like that. In theoretical world, we're not always going to be looking for those things. Like we just accept that they occur. All right. Now, just so you know, sodium hydroxide is a fairly common thing. Sodium hydroxide, if you've ever used borax to clean anything, borax was basically the cheapest version of detergents, and just about every laundry detergent, Tide, all of that has some borax in it. All right. If you've ever used hair relaxer or hair perm, it has sodium hydroxide in it. It's a common agent that it will do some stuff to your hair, it'll do some stuff to your skin and all of that. But the thing about sodium hydroxide, you don't want it directly on skin for very long because it will cause a chemical burn. If you've watched the movie Fight Club, you might have seen what that chemical burn can do. All right. Now, some symbols that we use in chemical reactions. The first symbol is, you'll notice there's an arrow. Instead of an equal sign, we will use an arrow. We call this the yield arrow. And yield in the terms that we're doing right now, the yield means to produce. All right. So that arrow, and whenever I say a yield arrow, I'm talking about yield, like yield meaning produce, kind of like in crop production, that you're creating something. All right. Another symbol that we will use is states of matter like solid, liquid, and gas, and those will relate to certain compounds. Liquid is really the main time that we're going to use liquid is if we're talking about water. That's going to be the main time and pretty much the only time you see liquid use. Solids, if we ever have a metal by itself, will typically be a solid. And then gases, we'll use gas for common gases that we know, like H2 is a gas, O2 is a gas, N2 is a gas. The other gases that we'll do that we typically know it as a gas is like CO2, things like that. And then the last one is this one, aqueous. Most of the ionic compounds that we will use in this class are going to be aqueous. So when I say ionic compounds, I'm talking about a metal reacting with a nonmetal. So aqueous indicates a solution that's dissolved in water. And if you kind of think about the Spanish or Latin root for water, what do you call water in Spanish? Aqua. And that's what that AQ. And Latin root is aquine or AQ. So that means water. And then another symbol that we'll see sometimes we'll see a triangle, and the triangle will typically be above the yield arrow, letting us know that there's a change in heat or a change in energy that has occurred. All right, and so it might be that the heat is required for the reaction or the heat is given off in the reaction. And it's letting us know that it's endothermic or exothermic, depending on the placement of that arrow. So chemical reactions, will have different things occurring and different symbols to show those reactions are occurring. Now, today we're not going to focus on these symbols that much because they're not going to be as important as when we get towards the end of the chapter. So, go back to your sheet, and based on what we've just covered, I want you to label that part B. I want you to label the product, the reactants, subscript, coefficient, and yield. So looking at your sheet, I want you to go ahead and label those things. All right. And so when you're ready, you can look up here and check your answers and see. All right. So the Mg plus the O2 is our reactant, and I misspelled reactant because I wasn't thinking. Forgot the N. All right. So the reactant is the Mg and the O2. The product is just the new compound that was formed, MgO. The arrow that's in between them represents our yield. Remember, yield is kind of like an equal sign in this case. It's just telling us that we have a before and an after. And then going down, the box that's pointing to that little small 2 next to the O is a subscript. And then the big 2 in front of MgO represents a coefficient. And then we're going to be using those coefficients to balance these equations. All right. So recall that the law of conservation of mass tells us that matter is neither created nor destroyed in an ordinary chemical reaction. So if I'm going camping and I take a log and I want to burn it, that log, when I burn it, that log is going to combine with oxygen in the air, and that's what we're seeing with the fire. So that fire is actually our brain's kind of understanding of what's happening when we have the chemical reaction between the materials in the log and the oxygen in the air, and we see that heat exchange as fire. All right. So as the log burns, we're going to produce 2 main things. We're going to produce ash, which is mostly carbon, and then we're going to produce the smoke, which is mostly hydrogen and carbon dioxide and carbon monoxide, things like that. All right. So we're going to be producing a lot of different little things there. All right. But that ash or that charcoal that gets produced is typically mostly just carbon, and then we're releasing H2, CO2, CO, some water vapor, H2O gas, things like that in there. But law of conservation of mass tells us that if I have 31 kilograms between my reactants, that means that my products also have to be 31 kilograms. And so the math that we were doing in last chapter is going to relate to what we're doing here and how we know that to be true and all of that. All right. So not really a lot that you should have to copy off of this one. Just remember what law of conservation of mass states. All right, that we can't lose mass in a reaction. All right, so now let's get to writing equations. All right, so there's different types of equations that we're going to use in this class. We're going to use a word equation, and that's the one that you should already be familiar with. A word equation is used to describe a chemical reaction using only words. Words describe the conditions, the reactants, and the products. And in a word equation, you're not so much focused on balancing. You're just telling me what's happening and what's present in the reaction. When we go to the symbolic, then we're going to start balancing. So all right. And so in word equations, we're going to describe what's kind of happening here. So I'm going to scratch this one out because balancing doesn't so much apply to the word equation. All right. So word equation is used to describe a chemical reaction using words. Those words describe the conditions, the conditions of the reactants and the products. Does anybody need more time for just those two statements? All right. So think back to biology, think back to early science. I want you to write the word equation that you've written for photosynthesis in the past. Remember, photosynthesis is the process that happens in the leaves. And so think about what we give off that trees and plants use, and then what can be found in the ground that trees and plants use, or maybe falls out of the sky that trees and plants use. And then what are the two products that trees and plants create? All right. And as you're writing it, can someone tell me what's happening in photosynthesis? What are the main reactants in photosynthesis? Carbon dioxide. And what is carbon dioxide going to react with? All right. All right. And what is produced? All right. So I want you to save that equation because we're going to come back to it in a minute. All right. So you've already seen word equations. You've seen word equations probably since second or third grade when you talked about photosynthesis, and you probably wrote it different ways, but it all comes down to going to be something similar to this. I know one of the common formative assessments that you have early on for some of the early sciences that you have to be able to drop and drag those words into boxes and be able to answer it. I just know I've seen it in the past. All right. So, steps to convert a prompt to a word equation. So sometimes you'll be given this word problem and we need to write a word equation from it. So we highlight the important parts of the word problem. We identify the reactants, we identify the products, and we write the formulas for the chemicals. All right, or we write the names of those chemical formulas. So So I want to be able to take a word equation and I want to be able to put it more symbolic. All right. So now we know how to use chemical names and we know how to write chemical formulas for them. So we can save some time. Now in this chapter, I'm going to have you doing all the steps just because I want you to see the relationship. But I want us to be able to go back and I want us to be able to take that word equation that we just created and create some sort of symbolic equation from it. So I want us to be able to go from a word problem to a word equation and ultimately go to a skeleton equation. All right. Skeleton equation is our unbalanced symbolic equation. All right. Does anybody need more time on this one? All right. So going back to our word equation that we just created for photosynthesis. If I wanted to change this to a skeleton equation, how could I write carbon dioxide symbolically? What phase of matter do we usually experience CO2 as? Gas. All right. What about water? How can I write water symbolically? H2O. And most of the time when we experience water, it's going to be a liquid. All right. This energy or sunlight, I know that I'm having to change the heat, change the energy in some form, so I can just write that as a delta H. This part is not going to always be included. All right, we're not always going to see this in a reaction. I'm just showing it here because you're familiar with it. All right, what about glucose? What is the chemical formula for glucose? C6H12O6. And in fact, on the worksheet that I had for empirical molecular, we actually solved for the molecular formula of glucose because I heard a few people mention, hey, that's glucose when you did it. All right. So, and then oxygen, how would we write oxygen as a symbol? O2. Big thing is to recognize that. So now we have this one. Looking at the left side and the right side, do the numbers match up between the atoms that are present? Well, first let me ask this question. Do we have the same types of atoms on the left side and the right side? We only have carbon and oxygen, carbon, hydrogen, and oxygen. They're both present on both sides. All right, but they're not present in the same amounts right now. So we have to satisfy the law of conservation of mass by having the same number of atoms on each side. Now, to be CO2, can I write CO2 can I write carbon dioxide any other way than CO2? No, because if I do, it's not CO2. Can I write water any other way and it still be water? The only thing I can do is change it to HOH, but I still have 2 hydrogens and 1 oxygen. All right, that I'm not worried about. Glucose. If I change that 6, is it still glucose? If I change that 12, is it still glucose? All right, so I can only write glucose this way, and I can only write oxygen this way. So I can't change those subscripts. So I have to find a way to balance the atoms without changing the subscripts. All right, so when we're balancing the equations, here are the steps to balance an equation. We're going to write the symbolic equation or the skeleton equation. We're going to count the atoms on each side. We're going to determine how many carbons, how many hydrogens, how many oxygens. And then we're going to balance the number of atoms and we're going to verify. the way that we're going to balance the number of atoms is by using coefficients. And then at the end, we're going to verify that we have the same number of atoms on each side. So if we can't change the subscripts, we can only change the coefficients. So we'll give us 2 more rules after this. So I want you to get these first. But write the equation, and we're going to call that a skeleton equation or a symbolic equation. We're going to count the atoms of each type of element on each side. We're going to balance the number of atoms using coefficients, not using. So let me go back. Using coefficients. And then we're going to verify that we have the same amount. All right. So does everybody have those 4 statements? All right. So 2 last things. Do not touch the subscripts. We can't change the chemical formula. So do not touch that. So carbon dioxide has to always be CO2. Water has to always be H2O. Salt always, or table salt is always 1 sodium, 1 chlorine. Those things have to stay how they're written because they're either written that way because of balanced charge or they're written that way because it's a molecular formula. The only thing that we can change, or the only numbers that we can manipulate, is a coefficient. So coefficients, again, will represent how many molecules, how many formula units we have. All right. So it's similar to what the subscript is doing, but it's telling us that we have more than one of that compound. So in the chemical reaction, it's actually representing a ratio of compounds to each other. All right. So let's go back to our photosynthesis equation. All right, and give everybody a minute to finish copying. So does everybody have this? All right, so let's go back to our photosynthesis equation. We have carbon dioxide plus water plus energy in the form of sunlight reacts to form glucose and oxygen. And so we rewrote that as CO2 plus H2O reacts to form C6H12O6 plus O2. All right. Notice I didn't include the sunlight because that's not important to doing this. All right. So we want to balance it. How many carbons do I have on this side? On my reactant side, how many carbons do I have right now? Just 1. On my product side, how many carbons do I have? 6. So that's out of balance. We recognize that being out of balance. How many hydrogens do I have on my reactant side? 2. How many hydrogens do I have on my product side? 12. All right, so that we know that's out of whack. And then oxygen, how many total oxygens do I have on my reactant side? 3. Notice I have them in 2 different places, though. And same thing over here. I have them in 2 different places, but how many total oxygens do I have over here? 8. All right, so I need to find a way to start reacting with it. What element do you think will be the hardest to balance because of how it's written? Oxygen. So I'm going to stay away from oxygen. I might even stay away from hydrogen right now because hydrogen's kind of funky too. But so I want to start with carbon. What's the easiest way to try to get carbon the same on both sides? I need to multiply. If I have 6 over here, I need to try to get 6 over here. How can I get 6 carbons over here? Multiply CO2 by 6, right? Put a coefficient of 6. Now, when I did that, that changed that to 6. What else did it change? Oxygen. So now I have 12 plus 1. Now I have 13 oxygens, right? Does everybody see how I got that? All right. So now, what's the next element that's going to be easy to manipulate, that's only in one place on both sides? Hydrogen. So I have 2 hydrogens here, I have 12 here. I want to get 12 hydrogens here. So what's the easiest way to get 2 to 12? Multiply by 6, right? So 6 times 2 is 12. So that changes that number to 12. What else did I affect? I affected the oxygen. So now I have 6 oxygens here plus 12 more oxygens. So how many total oxygens do I have on the reactant side? 18. All right. I don't want to do anything to this formula, because if I do anything to this formula, that's going to change everything else. So what's the only way that I can manipulate oxygen to get more oxygens? Change that. So I have 6 oxygens here. What plus 6 is going to equal 18? 12. So how can I get this number to 12? Put a 6 right there. So 6 times 2 is 12, plus 6 is 18. 18, everything's balanced. All right. Now, I wrote things down at the bottom because that was just helping us see the total numbers. You don't have to write that every time. So that was the way that I approached that. Now we can go back and verify. I can erase all my little work that I did down here at the bottom. I want to erase that. All right. I can erase all that and I can go back and check. I have 6 times 1, so 6 carbons, 6 carbons. I have 6 times 2 is 12, plus 6 is 18. I have 6 plus 12 is 18 for oxygen. I have 6 times 2 is 12, and I have 12. So I just go back and I verified that I have the right number of atoms. All right, now, so when we're doing this, the trick is to determine the number of each type of atom on the reactant and product side, and then we're going to, if we ever have any polyatomic ions, we're going to treat that if the polyatomic ion stays the same on both sides. So say maybe you have sodium sulfate plus calcium, and it reacts to form calcium sulfate plus sodium, something like that. Since SO4 stays the same on both sides, I can treat it as one singular thing. So balancing wise, I could treat that as an X or something like that. All right. But so on that one, the only thing I have to do is make sodium have 2 on the other side. And then there's another trick that if nothing seems to be working, if you keep coming up with a decimal for a coefficient, what you can do is one of the things, like on the last one that we did, we could have multiplied glucose by 2 and everything else would have worked out whole numbers then. And that's what I mean when in doubt, double it out. So let's look at this one together. So I have a prompt: zinc and lead nitrate produce zinc nitrate and lead. So writing that as a word equation, I can say zinc plus lead 2 nitrate produces zinc nitrate and lead. Changing that to a skeleton equation or a symbolic equation, how would I write zinc as a symbol? Zn, right? Lead 2 nitrate. So I'm going to kind of show you these as we're doing it. Symbol for zinc is Zn. Lead 2 nitrate means that I have lead with a +2 charge, nitrate. I think nitrate has a -1 charge, if I remember correctly, when I look at it. And so zinc, when it's in compound, zinc always has a +2. Nitrate is a -1. And then lead by itself, lead as a metal, doesn't have a charge. So that's the ions and elements that we're dealing with. So writing that as a skeleton equation, I have to be able to take my elements that are in compounds. So that lead 2 nitrate is an ionic compound. So I have to be able to switch the charges and get the right equation. Same thing with zinc nitrate. That's an ionic compound. So I have to be able to get the right ratio of elements in there. So when I write this, you're going to see something like this. Why for nitrate in both cases, why do I have a set of parentheses around it with a subscript of 2 on the outside for both of those? Because I need two of those polyatomic ions, because they're a -1 charge to offset the +2 charge for both lead 2 and zinc. All right. I know that lead is a +2 charge because it tells me with the Roman numeral 2. I know that zinc is a +2 because if I look at my common transition metals, zinc is always a +2 charge. And both of those can be found using your reference packet. All right. Now, the last step would be to balance this. What's nice is sometimes when we write our skeleton equation, sometimes it's already balanced. So if you look at this, do I need to do anything to any of these to balance them? I can go ahead and verify it. I have 1 zinc. I have 1 zinc. I have 1 lead. I have 1 lead. I have 2 nitrates. I have 2 nitrates. So in this case, my skeleton equation and my balanced equation are the same. All right. So this one, now I will say this. So in these, we never have to show the ones. But every once in a while, you will get a question on active, a question in Moodle, a question on the test, where it would say, what are the coefficients to this balanced equation? And it'll give you like multiple choice things there. So our coefficients for this would be 1, 1, 1, 1, because we have 2 reactants, 2 products. Every one of them has a coefficient of 1. So it'd give you a choice like 1, 1, 1, 1, or it might give you 1, 2, 2, 1, something like that. And you have to pick the best answer. So this one, all of the coefficients are 1 after it's balanced. Now, it doesn't necessarily give you the balanced equation, but if we understand that this one is already balanced, we can use that. All right, so let's do this one real quick. So aluminum bromide and chlorine produce aluminum chloride and bromine. Go ahead, write what you think the skeleton equation is and try to balance it. All right, before you balance, check and see if you got your skeleton equation correct. And I want you to think about the why it's written like it's written. All right. So aluminum chloride becomes AlBr3 because aluminum's a +3 charge, bromine's a -1 charge. And so when I react those as a compound, I need 3 bromines to offset 1 aluminum. Chlorine, when it's by itself, is diatomic. It's part of Brinkelhoff. So I'm going to write chlorine as Cl2. Aluminum chloride, same kind of situation. Aluminum always has a +3 charge. Chlorine always has a -1 charge because of their locations on the periodic table. So it's going to be AlCl3 because of balancing the charge. And then bromine is also one of the diatomics, part of Brinkelhoff. So you're going to write it as Br2. As it's written, is it balanced? Do I have the same number of aluminums on each side? I do have the same number of aluminums, but do I have the same number of bromines on each side? No. I have 3 here and 2 here. So what is the lowest common multiple between 3 and 2? 6. So how can I get 6 bromines on this side? So I put a coefficient of 2 there. How can I get 6 bromines on this side? Put a 3. Is bromine Is bromine balanced now? All right. So let's start working. Whenever I balance bromine here, what did I do to aluminum? I have 2 aluminums, so I need 2 aluminums here. And so that means I have 6 chlorines in my product side and only 2 on my reactant side. So how do I get 6 chlorines here? 3. Is it balanced now? All right. So I want us to take a look at the sheet that I just gave us. I'm only going to assign a couple of these. So you do that one. You do that one. And I want you to do that one. All right. How do we get out of here? $8:15. We only have about 5 minutes left, so we're going to start with those three tomorrow morning. All right, you can start looking at Chapter 7 active. Don't go past what we've done. So we've talked about word equations. We talked about sum balancing. If it's asking you to predict products, if it's asking you anything about net ionic or total ionic, leave those alone. If it's asking you to identify the phase of matter, I would leave that alone for right now, because I haven't told you the how and the why we know certain things. I've only told you base stuff at this point. But go ahead, try to do those three for tomorrow. That'll be where we start. And then we can start looking at some other things.